Hello, so we're doing the latest M1 IAL Edexcel paper, which was done in January 18. It's now May 18. It's warm outside, and you may hear some noises, dogs snoring and children playing, radio playing, but I promised a few people to do this video, so I think we'll just have to put up with those things. So we've got a standard free force kind of situation here. Something's being held by an inextensible string AC. We've got an inextensible string there, AC and BC. It's been held and you're given the angles, and we've got a weight coming down. So we just have three forces. I'm going to draw that separately up here. So we have the weight here, TA. Sorry, not the weight, the tension, TA. And we've got another tension here, TB, and we've got W. Mark on the angles, because this angle here is 45, this angle here is clearly also 45. Because this angle here is 30, we can mark an angle of 30 degrees here. Okay, so looking at the components, let's resolve horizontally first of all. Now I'm going to do this the more general way, which is what we normally do with statics problems: resolve vertically, resolve horizontally, or if it's on an inclined plane, resolve perpendicular, and resolve parallel, and then eliminate and things. But when there's free forces involved, there's often a quicker way using the triangle forces, or what's called Lamy's theorem. But let's do it the standard way, because I know some people always choose to do it this way, and in fact it's the main way that's marked in the mark scheme, if you have a chance of looking at it. Okay, so we're going to resolve horizontally. Let's look at the component of TA. That's TA cos 30, because it's next to this marked angle 30 degrees here. And the components of TB, going in the other direction, but the horizontal component is TB cos 45 degrees, because we're next to the marked 45 degrees angle there. So these are the only two horizontal forces or components of forces present, so we have these two must be equal to each other. So writing TB as the subject of this, because we're going to do a substitution in a moment, TB is equal to cos 30 over cos 45 TA. I'm not going to bother working that out at the moment, because we can do that on the substitution and the like. So now let's just resolve vertically. Okay, so we've got a vertical component of A, which must be TA sine 30, partly because we know the other one was cos 30, but actually it's away from the angle that we've marked 30 degrees on our diagram, so it's TA sine 30. Similarly, TB sine 45 is a component there, and they're balanced with the W force going downwards. Okay, so that enables us to write a vertical equation. So we have TA sine 30 upwards plus TB sine 45 also upwards equals to W. Okay, now that's it. So now we can substitute for TB. So we have TA sine 30 plus TB, we're substituting for TB, so that's TA cos 30 cos 45 which is basically TB is that. So I've substituted that times by sine 45 equals to W. Now I noticed, looking some people's work, that people have used calculators for this and worked with actual decimals. If you do that, be careful with your the way you present it also, and make sure you store the numbers, because a lot of these have got exact surd numbers. I'm not even going to use a calculator yet, because I can see that sine 45 over cos 45 is tan 45. And even better than that, tan 45 is 1. So I don't even know that, but I'm going to use it because we're allowed a calculator. So we can say, I'm going to use a calculator in a moment. Sine 30, let's take TA out as a factor, cos 30 equals to W. So TA is equal to W over sine 30 and cos 30. I don't think I've got anything to prove now. Obviously we could work with surds and without a calculator, but if we sub in 1 sine 30 plus over cos 30 on the calculator, you get the exact answer of minus 1 plus the square root of 3W. They did accept decimals, of course, so that you could have had 0.732W or 0.73W. So now we can sub back TA into our TB formula, which seems to have disappeared, but we had a formula which seems to have disappeared in the process somewhere, but when we did our resolving equation, we had a formula for TB which was equal to cos 30 over cos 45 TA. So now we can substitute for TA in there. So we've got TB is equal to cos 30 over cos 45 times TA, which we've already worked out as minus 1 plus the square root of 3W, and that equals to, if we put that into our calculator, it will give us an exact answer, which is minus the square root of 6 plus 3 the square root of 2 over 2W. Again, 2 or 3 significant figures was accepted. I think actually they accepted even more significant figures, but 2 was the minimum, so 0.897W, but they accept exact as well, so that's fine. Right, so that's probably the way most students have gone about it. I do think it's the longer way, and but you know, I suppose the thing is that works in all situations with statics, whereas what we've got is we've only got 3 forces here. So there's a couple of things I'm going to do now, which in my opinion are nicer and quicker. You could only use when you've got 3 forces involved in your diagram, and then you can use a quicker method, triangular forces or Lami's theorem. So let's look at alternative 1 using triangular forces. Oh, it's quite nice, but I say many students don't like it because they don't like constructing the triangle. We've got 3 forces here, W and TB and TA, which we can form a triangle for. If I start with W, I'm struggling to draw a straight line here. Not a lot better, but anyway, that's my W downwards. And then I've got TB. The next one I join there needs to go off in the right direction. So I could either draw TA going up in this direction here, or TB going in this direction. And since I haven't got any room to draw it there, I'm going to draw it this way. So that's T B in that direction with this angle 45 degrees. And then again I can now draw my TA in that direction there. Now this angle here marked is 30 degrees, the one I've just marked there, that's 30 degrees, but this angle here is 45 degrees because we've got a right angle triangle there. So this whole angle here is 75 degrees. I think this is what some people just don't like, playing around with the angles like this, but it is quicker than doing some of this. And then this angle here, well, we can see that this angle here would be 30 degrees, so this angle here is 60, and of course, I suppose we can also check that the angles add up to 180 degrees, which they do. Okay, so now we can use the sine rule. and we can say that TA times the sine divided by the sine of the angle opposite is equal to TB divided by the sine of the angle opposite is equal to W divided by the sine of the angle opposite. Sine 75. Okay, so now we can get TA and TB without having to do any substitution at all, because it all comes out in this. So, looking at TA, we're looking at this part of the equation here. TH over sine 45 is equal to W over sine 75. So TA is equal to sine 45 divided by sine 75. W, and that will give me my minus 1 plus the square root of 3W that I need in one go, or the 0.732 W we get in one go. And then we can do something similar with the TB. So TB, you're looking at this part of the equation. So we can say TB is equal to sine 60 over sine 75 W, and that will give us this answer here that we've already worked out, minus the square root of 6 plus 3 the square root of 2 over 2 W, or the 0.897 W, or the 0.90 W if you prefer. Okay, so that's one alternative, but some people don't like drawing this triangle because it's a bit fiddling around. I think it's fine, it's my favourite thing, but if you don't, then I suppose you can revert to this, which will always work, or there's yet another alternative, an old theorem called Lamy's theorem. Now Lamy's theorem doesn't require the triangle, we can just draw the forces as they are, so we have TA going in this direction, so that's TB going in that direction, and we've got TA going up here like this, and we've got W going downwards. And in this, if you use this method, what we want is the angles in between all of them. So this angle here will be, because the angle I've marked there is going to be equal to 45, this angle here is 135 degrees. Similarly, because the angle to the horizontal here is 30 degrees, this is 120 degrees. And this angle is going to be equal to the 60 degrees plus the 45 degrees, or the 105 degrees, check that they add up to 360. Okay? And so we didn't need to, all we need is the angles right between the forces if we use this way. It's basically a geometrical tweak of the sine rule, because what Lamy's theorem says is that the ratios of the forces and the angle opposite are equal. So in other words, we've got TA over sine 135 degrees, because the 135 is opposite it's not next to the TA, it's the one opposite on the other side, is equal to TB over TB, the angle opposite there is the 120 degrees, equals to W, and the angle opposite the W is 105. That always works with free forces as well. It's basically a neat little way of avoiding drawing a triangle if you don't like it, but it does require remembering that it's the angles in between that we want. It's called Lamy's theorem. Look it up. It's pretty easy to work with if you want. Also, I haven't put sine on those. Sine 120 and sine 105. You may notice it's very similar, because really it's a geometrical tweak. As I say, sine 45 is the same as sine 135, because 45 plus 135 equal 180, and sine 60 is the same as sine 120, because these are 180, and so on. So you can see it's the same, amounts to the same thing. So we would get, in a similar way as we did before, TA is equal to sine 135 over sine 120. TB, which is equal to minus 1 plus the square root of 3W. And, sorry, that's W, so there. That should be W. And it should be sine 105 there. Listen a bit, but basically I'm doing the equivalent in the second line. So sine 135 divided by sine 105, and TB is equal to, looking at these two, sine 120 over sine 105 times by W, which gives me my minus the square root of 6 plus 3 the square root of 2 over 2W, which we had before. So spent a long time on that question, but I do think it's good to look at alternatives to the main way, which most, probably 80% of students are doing it in this longer way, because that's the more general way which will work with other cases. But if you can work your way with triangular forces, or even Lami's theorem, it can save a bit of time. Okay, so let's have a look at the next question. So this is another statics question really, because it's talking about the particle being at rest, but we don't have three forces anymore. We've got four forces, because we've got friction as well. We've got the force coming down of 20 newtons here. We've got a reaction force which is acting perpendicular to the surface. We have the weight of 40 newtons working downwards, and we've got a friction. I'm not going to call it mu r at this stage, because F is not equal to mu r. We're not told it's in limit equilibrium. We're basically, we're going to be using the general relation between F and mu r, which is F is less than or equal to mu r. Remember, F is only equal to mu r if it's moving or on the point of moving. Okay, and it doesn't talk about that here. It just says it's at rest, it's in equilibrium. I'm going to mark that as F. Okay, so we definitely do resolve horizontally and vertically in these cases, and we've got this angle as theta. So let's resolve horizontally, and what we have is the F and the component of the 20 balancing, one going one way and the other going the other. We look at the 24 Newton force. Okay, so the 20 Newton force, the horizontal component, because it's marked on next to the theta here, is 20 cos theta. So we have F is equal to 20 cos theta. Okay, so that's the horizontal component. Looking at the vertical, horizontal equation, looking at vertical, we've got R going upwards and we've got 40 going downwards, but we've also got the component of this 20 Newton force. And that component there, because it's away from this marked angle here, is 20 sine theta. So we have R going upwards equals to 20 sine theta plus 40. Going downwards. Okay, so those are our two resolving equations. Now, we do not, let's say we do not use F equals to mu r. The general relation is F is less than or equal to mu r. So if ever you're asked to, this comes up in M2 more common than M1, but if ever you're asked for a relation with an inequality in it for mu, you're using this relation because it's not on the point of this. It's a general equilibrium. And in general, this is the case because friction is only equal to mu r if it's on the point of moving or moving. So if it doesn't have to reach its maximum, it won't. So that gives us our inequality. So we just have to put these things in here. 20 cos theta is F, is less than or equal to mu times 20 sine theta plus 40. So we can divide, so that gives us mu is greater than or equal to 20 cos theta over 20 sine theta plus 40. Okay, so we can divide top and bottom by 20, sorry, so we get mu is greater than or equal to cos theta over sine theta plus 2 as required. Nice question. Quite a few people got the resolving right, but didn't really get the final couple of marks properly for not setting it up as an inequality using this. And that's what you should always do if the question is asking you to prove an inequality, use that relation. Okay, let's have a look at the next question. Okay, so we've got a momentum and impulse question. We've got two particles going in the opposite direction towards each other. We're given the velocities 2u and u of them going towards each other. Particle A, which is of mass 2m, is moving with speed 2u, and particle B, which is of mass km, is moving with speed u. Then during impact, often we like to draw the impact thing as well, so in the directions of the impulse of each one, you have that happening. And then afterwards we're told that they both reverse as well. They both reverse, so A becomes that, and it tells us that that has speed u over 2, and it doesn't tell us the speed of B. And we're going to use that for, I'm going to call it V. I'm going to use that for part B. Okay, so let's move over here now. We want to use for part A the impulse equation. I is equal to mv minus u, bracketed. Right, so we need to be kind of careful, notoriously difficult with signs with the impulse equation. Looking at the direction of the impulse on A, we need to be careful, because if we look at it, the force on B and therefore the impulse on A, of B on A is in this direction here. So it might be easier to regard this way as positive on A. So we're going to apply the impulse equation. So any forces or impulses that are in that direction we're going to call positive. Okay, and then apply the impulse equation and it should work out, but you have to be very careful with signs. So the impulse is equal to m, which in this case, because we're looking at particle A, so we're doing this on A, is equal to 2m v. Now v is equal to u over 2, because that's the final velocity of A. And notice it's going in the positive direction, because we're taking this way as positive. So that's positive u over 2. Take away, because it's in the formula, the initial velocity, which is this 2u here. But that's going to be negative because it's going opposite to the direction we're applying the equation in. So that's negative 2u. Now people say, well, what if I apply in the opposite direction? It will work, but then you would have to, your equation would look, so you're either going to do it that way, which I think is probably easier. But if you wanted to call this way positive, your equation is going to be looking like this. Minus I is equal to 2m, then it would be minus u over 2, and then we would have plus 2u. Okay, or we would have, so yeah, or would it be something like that? Would it be? Oh no, it'd be negative u. So negative 2u. And we could either put a negative there, in which case we'd get the magnitude, or leave it like that, and we'd have a negative answer for the impulse, and then we'd have to make it positive. So that's probably more confusing than anything, but just be careful with the signs. Take it in this direction. I always say take it in the direction in which impulse is actually acting on the particle you're using the impulse equation on. So here, if we multiply that out, we get I is equal to times that these two cancel to give positive, so that will be U plus 4U, or mu plus 4mu, which is equal to 5mu. Okay, that's the correct answer for that. A few mistakes I've seen on those, but more problems we found with part B. A little bit unusual for those who've done M2. It's not that it is an M2 question, but you see this type of thing where you're setting up an inequality in a momentum situation more often. I'm going to use, you can use impulse, but generally speaking prefer to use momentum as an equation. So if we use momentum, and now I'm going to do the opposite to what we did before, I'm going to call this y positive. Okay, and we're going to get an expression for v, or with k's in it. And I'll tell you what we're going to do about that in a moment. We're going to get an equation with v in it. So we have this here, 2m times by 2u. Okay. Now this one's going in the opposite direction, so that's minus km times by u. Okay. This one's also going in the opposite direction, so that's minus u over 2 times by m times 2m times minus u over 2, plus this one's going in the positive direction, that's kmv. That's the m1v. Right, now m's cancel, so I'm going to get an expression for v. So let's multiply this out. That's 4u minus ku is equal to minus u plus kv. So that gives me kv is equal to 5u minus ku, which gives me that v is equal to 5 minus k over k times u. Right, so what we're going to do with this? Well, the point is, the question says that the directions of the things are reversed. So v has got to be going in this direction here, and we've set it up, this one up with the positive being in this direction. So v has got to be greater than 0 because it says the particle's reversed, and that's how we set up our inequality. So we use the fact that v is greater than 0. So we have 5 minus k over k times u is greater than 0. Well, we can divide by u times by k. We get 5 minus k is greater than 0, which gives us k, with some 5 is greater than k, if you like. But we're to see it that way, so k is less than 5 is our answer. So that's how we did that question. Probably okay when you see it, but a lot of people haven't seen that in M1 very often, that type of thing in M1 very often. Which is probably why the question stumped quite a few people. Okay, let's have a look at question 4. Okay, question 4 was a pretty straightforward dynamics question, single particle on an inclined plane. The most common place where people lost marks here was actually rounding errors, which I'll talk about later. But anyway, we've got a particle of mass 6 kilograms, so that means it's got weight 6g, inclined at angle 30 degrees, which means the angle here is 30 degrees. And we have r here, and we're told it's on a rough plane, and we're given a coefficient as a quarter higher, and we're told it's accelerating. So unlike the question we saw, question 2 earlier, we can assume F equals mu r because it's moving. In fact, I'm just going to call that force there quarter r, put it on the diagram like that. Although you can call it F and then use F equals mu r when you're working, but it's perfectly okay to put on your diagram. and you will get your method mark for, because often there's a method mark associated with using f equals mu r. So even if it's seen on the diagram, you'll still get it. Right, so, and it's accelerating downwards, so it's finding accelerating, so it's pretty standard stuff. There's a component of the weight going down the plane, and we need to resolve perpendicular, because there's no movement perpendicular to the plane here. So we have r equals to 6g cos 30, because we're looking at the component of the weight into the plane like that, 6g cos 30. Okay. But if we're looking at the component down the plane, which we need to apply a f equals ma, the component down the plane is 6g sine 30. So we can say f equals ma down the plane, parallel to the plane. We have 6g sine 30 minus a quarter r equals to 6 times by the acceleration, mass times acceleration, 6a. Right, so if we sub for r, we get 6g sine 30 minus a quarter times by 6g cos 30 equals to 6a. Now we can use a calculator here, but I just always have an overwhelming temptation to cancel anything, even if I'm going to use a calculator. So I'm going to cancel the 6. So that gives me a equals g sine 30 minus a quarter g cos 30, which if you put in the calculator, it actually gives you an exact answer, but we want it to have 3 significant figures, 2 or 3 significant figures. 2.78. Okay, a few rounding errors crept in at this point, where I saw a few which were 2.7. I saw a few 2.77s there, but actually most people got that mark, okay, but then missed out on an accuracy mark in the next part, because this is actually 2.7782377761, or exactly 196 minus 49 square root of 3 over 40. So if you use this 2.78 and not use the stored answer from before, you're going to get a rounding error, because you prematurely used a rounded answer. Okay, I'll show you in a sec. Let's just move this over and make a bit of space for myself. Okay, that's better. Okay, so now we can do for part B. Well, it's very straightforward. We've got it moving 10 meters down the slope. We know that the initial velocity is 0, because it says it's released from rest somewhere. Yeah, from rest. We want to find the speed it passes at a certain point, which is 10 down, and we have an acceleration which is 2.78, but just as I said before, it's not exactly 2.78. If you put 2.78 in your calculator, you're going to lose a mark. So it's v squared equals u squared plus 2as. So that gives me v squared is equal to 0 squared plus 2 times 2 point, it's actually 77 blah 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 times by 10. And when we work that out, it gives us an answer of, let's just get it up here, 7.45 to 3 significant figures, or to 2 significant figures. The actual answer comes to 7.5, which is also okay, of course. But we saw quite a few 7.46s, because, as of what I said, people used the number 2.78 exactly rather than the full calculator answer from before, so lost a mark for writing 7.46, premature rounding. Okay, so that's the main point. Most people got marks there, and the main place where marks were lost was on rounding at the end. Okay, let's have a look at the next question. Okay, so we've got a cyclist, it's a speed time graph question, cyclist moving along, accelerating, then going at constant speed for 40 seconds, and then decelerating for a time. Now it's tempting, because we often see this kind of trapezium type shape. Here it's tempting to draw the trapezium around, but in fact what happens here is that we're not told that, in fact it isn't, we're told that it stops at some place on the road at point B. We're not told that that is at the same time, just stops suddenly before would have come to rest anyway. So at some point B on the road. So the graph looks a bit like that at this stage. Now that wouldn't get full marks at this stage because we do need to annotate with the information that we're given. We're told that it accelerates for 20 seconds here, and then the constant bits you can either write 4t plus 20 there if you want, or you can mark it as a kind of distance between 2 points on the graph. That's fine as well, 4t. And then this cyclist then decelerates for a time t here. Okay, and then the next thing is to find the value of t, and what we're doing is we're using some information about the accelerations and that the total distance is 705. Okay, well, if we look at we certainly need to work out the speed that this is at, but we are told the acceleration is 0.6 for 20 seconds. So 20 times 0.6, it's easy enough to work out that as 12. Okay, now I suppose the key thing in here is what's going on in this last section, because we don't know, well, not directly, we can work it out, but we don't know the speed that the cyclist has kind of decelerated to when it reaches this point B. But we can use V is equal to U plus AT for that. Don't normally say use that equations for speed time graph questions, but in this case it seems, for this section, seems like probably the quickest way of doing it, to work out an expression for what the velocity is. We've got U is 12 and it's decelerating at 0.3 meters per second for a time t, so that's V. So this point here is 12 minus 0.3 t. There. Well, that's quite important because we're going to need to set up an equation for our whole motion 705, so there's quite a bit to do here. Well, let's just do it bit by bit. For this triangle, that's easy enough. That's equal to half times by 20 times by 12. So distance, what we're using is distance equals area here. So that's that triangle. Then we have the rectangle here. Again, not a problem. That's 4t times 12. But then we've got, let's just deal with these bits here. I'm going to split it into, could use a trapezium, but I'm going to split into this triangle here and this rectangle here. Now we know that this height here is 12 minus 0.3t. This therefore would be the difference, because it's going from 12, this whole distance here is 12, this must be 0.3t here, because the total of this and this has to be 12. So that's 0.3t, that height there. So we've got this triangle and this rectangle, and a lot of people missed out one of these terms, or they didn't recognise that this was a trapezium, which was obviously the other way of tackling this. So let's look at this rectangle here. That's t times 12 minus 0.3t. And then this triangle here is a half times by t times 0.3t. And that all equals to 705. Okay, so that's our equation that we need to solve. Let's multiply all these terms out. This term here is equal to 120. This is equal to 48t. This here is equal to 12t minus 0.3t squared, and this t squared, and this here is equal to 0.15 t squared is equal to 705. Now, the thing is, this is quadratic. Let's just bring all the terms together and bring them over to the other side. We'll get 0.3 t squared and 0.15 t squared. Bring it over and take into the other side. We'll come to 0.15 t squared. We've got 48t plus 12t, which is 60t. And 120, 705 take away 120, which is 585. That equals to 0. Right, now you can put out your calculator and get a solution, put in a quadratic formula and get a solution for it, which is fine. But I just have an overwhelming urge to do it without a calculator. Divided by 0.15. Don't have to do this, of course. You can just go straight to the formula at this point. That's t squared. Divide that by 0.15, but divide by 15 is 4, so divided by 0.15 is 400, and divided this by 0.15, a little bit less straightforward, is 3,900, equals 0. Now this factorises, I've got sign wrong here, that should be minus 60 when we take it over the other side, so that should be minus 400t there. So then we can factorise this. T take away 10, t take away 390 equals 0. Obviously t is not 390, it's an unrealistic answer, and of course nothing would work here. You'd have negative speeds here, so we know that t equals 10 meters per second, which is the answer to that part. Okay, so that's that part done. Doing the next part, well, if I quickly draw the graph again, it now says that the person will go uniformly to rest there. So we can basically add in this bit on there. So what I'm going to do is just work out this extra time here, call it little t. We already know that t is equal to 10, so we know this length here is 40, 4 times 10, and we know that this length here is 20. So we can work out t easily enough. Again, we could use v is equal to u plus at, or we can use gradient is equal to acceleration. Either way, we've got v is equal to u plus at. The final velocity is 0, the initial velocity is 12, the acceleration is minus 0.3 times by this extra time. That gives us 0.3t is equal to 12, t is equal to 12 divided by 0.3, which is equal to 40. So that gives us a total time, looking along this stretch here, is equal to 20 plus 4 times t, which we've worked out before, which is 10, plus 40, which is equal to 100 seconds. Okay, so that was question number 5. Let's have a look at question 6. Okay, so this is a forces and vectors question. The first bit is we've got two forces. So we're going to apply F equals ma because we're asked for the acceleration. Remember, F equals ma means resultant force, so we can just add these two forces together. So 2I plus 3J plus 4I minus 5J is equal to mass times acceleration. We're talking mass is 2 kilograms, so that's 2A. So that gives me 6I minus 2J is equal to 2A. So that gives me A equals 3I minus J. But don't be, quite a few people forget to answer the question. What's magnitude? So the magnitude of A using Pythagoras is 3 squared plus 1 squared, basically squaring the components of those and adding them and square rooting them. That's equal to the square root of 10, which was accepted as a final answer. Safer to give three significant figures as well though, 3.16 meters per second squared. Very generous about not giving units, by the way. Not normally penalised for lack of units, but I'll put them in anyway. Okay, so that's part A, nice, easy, straightforward really. Part B, if you know what you're doing, is also pretty straightforward. It's a V equals U plus AT, and we've got everything, we basically plug everything into this. We're told, we know it's accelerating with this acceleration we've worked before. We don't know the initial it started with, but we do know that after a certain time it's there, so we just put everything in and just hope that something falls out. So the final velocity, so that's our V basically, and this is our U, and T is capital T, and acceleration, as I say, is this here. So putting those into V is equal to U plus AT. So 10I plus 2J equals to U, which is minus UI plus UJ, plus A, which is 3I minus J times capital T. Right, now reorganising the right hand side a little bit, I get 3T minus U, or minus, let's not reverse the order like that, so minus U plus 3T times I, and UJ minus T, so U minus TJ. I'm not a U underneath it, what am I doing? U minus TJ, and a plus in between. Oh boy, don't ever miss out a plus sign in between those two. People think you're not, people think you don't know what you're doing. It's an expression here, and we need the plus there. Right, so now we can compare I and J, because if they're equal, I and J have to be equal. So we have minus U plus 3T equals 10, and U minus T equals 2. So I can add those two together. 10, it looks like a 16. So add those two together. I'm going to, the U cancels and I get 2T equals 12. That gives me T equals 6. Once I've got T equals 6, that's my answer to 1. It's easy to put 6 back in here. You get U is equal to 2 plus 6, so that gives us U equals 8. So we say, as long as you tackled that properly, it was nice, easy marks, but quite a lot of confusion. Some people put in the actual magnitude of the acceleration here, but vectors in this, and obviously going to be highly, not going to get any marks for that type of thing, because it's just not right. Okay, so let's have a look at the next question. Okay, so here we have a moment's question. First part is, well, we've only got 3 forces, so it shouldn't be too bad. We're told the reactions at RC and RD are related, that this one, D, is twice as much as the one at C. It says that somewhere in the writing here. There we go, twice the magnitude there, so we're told that. The key thing here, don't come up that often, but it's a non-uniform route, so the centre of mass is some distance x along here. Okay, and the weight is 8g. Now it always amazes me how few people, when it's such a situation like this, just do not use the most simple facts that we can get. And so applying moments equations left, right and centre about multiple places, we really don't need to. In this case we can just resolve vertically. It's not going to be very hard at all, and you're going to get 2 marks for writing this, which is pretty generous. But if you want to write a moments equation, you're going to be making life quite hard for yourself. So R is equal to 8 over 3g. So I'm going to write it, so then we are going to need a moments equation. I'm going to take moments about A. I know it's going to have more forces involved, but we're told that the distance AG is x. So I'm going to mark on the distances. The distance from A to C here, that's 1. The distance from A to D there, that's obviously 5. And the distance from A to G here is the unknown x that we want to work out. So taking moments about A, it's also easy to see which ones are clockwise and which ones are anti-clockwise. Obviously the 8g is going clockwise and the R and the 2R are going anti-clockwise. So we have R times 1 plus 2R times by 5 equals to the clockwise moments, which is 8gx. Now bringing these two together, that's 10R plus R, so it's 11R is equal to 8gx. Now, but we can sub in R at this stage. So we have 11 times 8 over 3g is equal to 8gx. And the 8 and the g cancel. So we're left with x is equal to 11 over 3 as required. There we go, 6 marks for that. But say, don't make equations complicated unless you have to. So that equation is a good one to use. And I think the same happens here where we're resolving vertically for the next part. For the next part we're going to need a new diagram because the point is the support is being moved so that AF is equal to 2. Let's write it below so I can put the force in. And we've still got, where was that? That was D below there, which is 1 from the end there. And we now know the centre of mass of this one, these distance. We know that this distance here is 11 over 3. Okay, because we've worked that out from the question before. Now we're told that it's not 2 times but k times ratio. So we've got the reaction, if we call that R, we are told it's some ratio KR, and the question is to find the value of K. Again, it would seem to be a very sensible thing. The weight is 8g. Oh, we've got a weight of 3g now marked at this point here. Now, it would be a sensible thing, I think, again, in this case, not always the case, but so often it's sensible to resolve vertically. So we've got R plus KR equals to 11g. Okay, we're going to use that later, but that's going to be a useful equation for us. But then we we want to take a moments equation. Now, there's various options. Because I've got a k in this equation here, I don't really want a k in my moments equation, so I'm going to take moments about d. Okay, it's not that it's impossible to take most about anyone else, but that just takes out the k in this equation, which probably makes life a bit easier. So moments about d. Now first of all, I know that this distance here, as I've said, is 11 over 3, but this distance here is 5. Okay, so the length from here to here then must be 5, take away 11 over 3, so that's 4 over 3, and then from there to there, so that's 4 over 3. Okay, now this distance now has changed because it's 2 there and it's 1 there, so that must be 3 meters to the r there. And then the distance from here to here will be 6 take away 1, because 1 is that distance, so that distance is 5. So I'm now going to take moments about d. So looking at the two anti-clockwise ones, we've got 3g times 5, force times distance, plus 8g times 4 over 3 is equal to 3r, the clockwise moments. Okay, well, that's 15g times 345, and there's 32 on the top, so that works out to be 77g over 3 is equal to 3r. So r is equal to 77g over 9. Okay, so now we can substitute for r into the equation we had earlier. So it just makes life easier that there's no k in this, which is why moments about d was the right way to go. So we have 70, so we're subbing for r. We have 77 g over 9 plus k times 77 g over 9 is equal to 11 g. Okay, I'm going to divide by 7 and divide by g, cancel out g from this. So we're cancelling out the g, and we're cancelling out 11. That would make divided by 11, which makes that 1, makes that 7, and makes that 7. So we have 7, tidying that up a bit, 7 over 9 plus 7 over 9k equals 1. So we have 7 over 9 is equal to 1 minus 7 over 9, which is equal to 2 over 9. So there's a k there, 2 over 9. So that gives us k is equal to 2 over 7. Okay, one more question to go. Question 8. Here we have a connected particles question, like often we get in these papers. Right, so let's just put some forces on this diagram. We're smooth, so we don't actually need to work at the reaction force there, because it's smooth, and so we don't need to work out friction, because there isn't any. There's a tension and a tension there, and there's the angle 40 degrees there. So we're going to apply F equals ma to both particles. To the A mass there, we've got the component of the weight going down. Remember, it's going to be accelerating this way for sure, because it's a 5 kilogram mass and it's the only way it can go. So that there, so that's A. So we're applying F equals ma to A. We've got T pulling it upwards. We've got the component of the weight down the slope, which is 3g sine 40, is equal to mass, which is 3, times by the acceleration, which is A. Then if we do the same thing for B, well, the mass is 5g, the weight is 5g, so the mass is 5. So that's 5g minus t is equal to 5a. Now I know you're not asked for acceleration, but it's highly likely we're going to need it for the next part anyway. So we're going to work out acceleration and therefore work out t for part A. So if I add these two together, we get 5g minus 3g sine 40 is equal to 8a. And working that out, we have A is equal to 3.762 blah blah blah, which I've stored in the calculator because you're not actually asked for that answer anywhere, but we need to use it at least once in our work, I think twice. So I've stored it in my calculator. And then t, to work out t, we can just rearrange the equation B for the equation motion for B. So that gives us t is equal to 3 times 9.8. Take away 5 times 3.762 blah blah blah. I'm just putting in the stored number I've got in the calculator, and that comes to three significant figures which I'm given. 2 is also fine, 30.2 newtons. Okay, nice easy 6 marks at this stage in the paper. In fact, I found from students I've been marking, they've often been picking those marks up later on when other questions have proved more challenging. So that part was normally fine. And so was part B as well, really. It says that it's falling for 1.5 seconds. We basically know therefore that t is 1.5. We know the acceleration that we've got. As I say, I've got that stored in the calculator. I'm not even going to use 3.762. I use the stored number on the calculator. And we know that it's starting from rest. It says somewhere that it is started from rest. Release from rest, there you go. And V is what we're being asked to find. We're being asked to find the speed that it rests at. So using V is equal to U plus AT. So V is equal to 0 plus A, which is 3.762 times by the 1.5, and that gives us to three significant figures 5.64. Again, I'm likely to need that a more accurate, significant figures there. So stored on my calculator, I also have the number 5.644133302. But we want 2 or 3 significant figures when we present the answer there. Okay, so that's again up to 9 marks, pretty okay, and then a little bit more to do for the final 5 marks. Now, this is slightly different. It's given us the time, but we see this kind of scenario a lot. What happens is it hits the ground after 1.5 seconds. So we need to work out how far it's travelled when this is moved down 1.5. I might do another diagram. So basically we need to work out when this has hit the ground here, how far this has travelled, because this one will have already travelled that far. So, and then what happens is this one will carry on moving, but it will start decelerating down the slope because the string will become loose. So to find the distance whilst accelerating, so the string is taut, basically, the string taut. So you've still got tension pulling the thing up. So we could have just apply, what do we know? We know that t is 1.5. I'm going to revert to not use this answer here because I'm use what I've given in the question. T is 1.5. A is the 3.762 blah 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 that we've used before, and U is 0, and we want to work out the distance, so we use S equals UT plus half AT squared. So we have S is equal to 0 times T plus a half times that 3.762 times 1.5 squared, and that equals to 4.233. Now that's not the final answer, that's just the distance it's moved, and again I've got that stored so that I'm not going to get around an error. The actual answer is 4.233099976 that I've got stored in the calculator, but I'm not writing it down. You make it look a lot nicer if you just store things in the calculator and use more, not exact, but the calculator with 8 significant figures on it rather than just using rounded answers. Okay, so that's the distance it's moved whilst accelerating. We need to find deceleration when B hits floor, basically, or after B hits floor. Basically, if we look back at this original equation here, we'll have everything here except the T, because there won't be a tension in the string anymore. So we'll have all this stuff here, but no T. So we'll put our F equals MA equation will be minus 3G sine 40 is equal to 3A. Well, that gives us A equals 2. And again, it's stored. You get the idea. It's minus 6.299 or approximately, but I've stored it on the calculator. Now we need to work out this extra distance it travels, because basically what's happening is you've got, at this point here, it's going to go an extra bit of distance here to here. Let's do the diagram again. It's already travelled this distance whilst it's accelerated. We need to work out the distance now where it travels whilst it's decelerating, that extra distance there. We've got the acceleration or deceleration is 6.299 down the slope because it's now slowing down. We know this distance here, which we're going to add on at the end. We know it's already travelled, that's when whilst it's been accelerating. We know we've worked out in an earlier part of the question the speed here. It now becomes u because it's the initial velocity at the point when it starts to decelerate. So that's 5.64, but again, it's not exactly 5.64. I've got it stored on the calculator. So we've got that, we've got the deceleration, and we want this extra distance. So we've got S, question mark, U is 5.64 approximately, V equals 0, and then we have the acceleration, as decelerated, minus 6.299. So we're going to use V squared is equal to U squared plus 2AS. So 0 squared is equal to that 5.64 squared plus 2 times minus 6.299 times S equals to 5.64 squared over 2 times 6.299. that comes to 2.53 to two significant figures, but let's just, it's actually 2.528 blah blah blah. Again, I've stored that. So the total distance is these two numbers added together. So that's the 4.233 plus the 2.528, and to three significant figures, when we work that out, that comes to 6.76 meters. Okay, so that's it. Okay, that's the most recent M1 paper, and probably the last one I'll be doing. Okay, bye, hope it was useful.